Hello everyone, welcome to the series of videos on pre-calculus. Before I begin, I just want to tell you that when you're watching these videos or when I created this video, my expectation is you already have the basic concept of college algebra. We'll spend some time on algebra part of the pre-calculus and we'll focus or we'll spend more time on the trigonometric part of the pre-calculus. So we'll start this chapter with function. In this video, so we'll look at the definition of function. We'll look at some examples whether that relation represents a function or not. We'll evaluate function at a given value. We'll find domain and range from the equation and graph. We'll look at piecewise function. We'll also look at the intervals where the function is increasing, decreasing, or constant, and also we'll see local maximum and minimum. So let's start with the definition of function. So before I look at the definition of function, so let's go ahead and see what relation is. So if you look over here with this definition, it says a relation is a correspondence between the first set called domain and the second set called range, such that each member of the domain corresponds to at least one. So at least one member of the range. So this is what it means. So let's say we have two sets. The first set is called the domain, okay, and the second set is called the range. Now let's say I have some members in the domain or elements in the domain. Let's say I have A and B, and then I have some members in the range. Let's say I have 1, 2, and 3. Now let's say A is associated with 1, or A is mapped to 1, or A corresponds to 1, and then let's say B corresponds to 2, and then let's say A again corresponds to 3. So based on this definition, so each member in the domain or each element in the domain is mapped to at least one member of the range. It could be mapped to more than one member of the range, but it has to map at least to one member of the range. Okay, so here if we see A is mapped to 1 and 3, so it's at least mapped to one of the members. So B is mapped to 2, so that means this is a relation. That's all. That's simple. The relation is okay. Now, when we look at function, function is a little bit. It is a little bit different. It's a special case. Okay, so the definition is almost same exact. If you look at the last part of the definition, it says each member of the domain corresponds to exactly one member of the range. So this is how we can show an example of the function. So let's say we have domain, and then we have a range here, the second set. Let's say in the domain we have, let's say 1, 2, 3, 4, and in the range, let's say we have 4, 5, 6. Now, let's say 1 is mapped to or 1 is associated with 4. Let's say 2 is associated with 5. Let's say 3 is associated with 6. And then let's say 4 is also associated with 6. Now, let's see if it satisfies our definition. Okay, it says each member in the domain is mapped exactly to one member in the range. So if you look at 1, 1 is mapped to 4, so it's just mapped to one member in the range. 2 is mapped to 5, so it's mapped to exactly one member in the range. 3 is mapped to 6, it's exactly mapped to one member. And 4 is mapped to 6, that means 4 is also mapped exactly to one member in the range. So this is a function. So it basically means when you say a function, if you give me an input, I can give you an output which is just exact. The output is unique for each element. Okay, the output is exactly one. There are no two outputs. So this one is not a function. It's just a relation because in this case, A has two different outputs. That's why it's not a function. So for a relation to be a function, each input must have exactly one output, or each input must be mapped to only one output. It cannot be mapped to two different outputs. So that's what a relation makes a function, okay? Now, there are different ways we can represent a relation. The first one is verbally, or you can just write the description in words and you can represent that relation as a function. We can also represent a function algebraically by writing a formula. So for example, we'll see that later. So f of x equals x squared or something like that. Okay, we can write a formula, explicit formula, and represent a function in algebraic way. So the next one is visual. We can either represent a function by a graph or this mapping diagram that I just drew up here. And then we can also represent a function numerically in a table. So for example, this one, the first relation, we can also write these in order pair. So for example, this one, we can write this relation is A comma B. That means A is in the domain and the corresponding member in the range is 1. And I can write, sorry, A comma 1. And then A comma 3. And then B comma 2. So I can represent that way. So I can write this one in order pair, this function as 1 comma 4, 2 comma 5, 3 comma 6, and 4 comma 6. So that means this is representing numerically as order pair. So the first number in the order pair represents the element in the domain, and the second number represents the element in the range. Our first one is the input, and the second one is the output of the function. So let's look at some examples here. So we are given different relations here, and we need to identify whether it's a function or not. So maybe it's easy to determine that if we draw the mapping diagram. Um, so for the first one, let's write domain. Okay, so domain, in the domain we have the first number, so 1, 1, and 2. So we don't have to repeat that, so we can just write 1. So we have 1 and then 2. And in the range, we have 5, then we have 10, and then we have 25. So now let's draw the, let's map this, okay? So 1 is mapped to 5, and then 1 is again mapped to 10, and 2 is mapped to 25. So we see here that the input 1 has two different output. So it's not mapped to exactly one output. So that means this is not a function. It's not a function, it's just a relation. Still a relation because each input is mapped to at least one output. So the domain, we can just list the domain. So domain are the elements in the first set, which is 1 comma 2. Again, if you have repetition, we just write it once. And the range, we have 5, 10, and 25. So that's the first one. Let's look at the second one. Let's write the domain. So here in the domain we have 0, 1, 2, and 3. In the range we have 0 again, 2, 4, and 6. Now if we draw the mapping, if we map this, so 0 is associated with 0, 1 is associated with 2, 2 is associated with 4, and 3 is associated with 6. So here each input is mapped to exactly one output. That means this is a function. Okay, so it is a function. In the domain here are the elements in the first set, so 0, 1, 2, 3. In the range 0, 2, 4, and 6. Now let's look at the next one. Again, let's draw that mapping. So domain, the domain we have 0, 1, -1, 2, and -2. Then range, we have 0, 1, we have another 1, so we just write once, then 4, and we have another 4, so we just write once. Okay, so now if you draw the mapping, so 0 is mapped to 0, 1 is mapped to 1, -1 is mapped to 1, 2 is mapped to 4, -2 is mapped to 4. So now here, if we look at 1 is mapped to exactly one output, which is, sorry, 0 is mapped to exactly one output, which is 0. 1 is mapped to 1. -1 is, so each input has exactly one output. Though we see that two inputs go to the same output, but it does not matter as long as we have um, each input mapped to exactly one output. It doesn't matter if we have all the inputs going to the same output. It really doesn't matter. So this is still a function. So it is a function. Now let's write the domain. 0, 1, -1, 2, -2. In the range, we have 0, 1, and 4. Okay, so now that's how we determine if you are given an order pair, okay, whether it's a function or not. But if you are given a graph, how do you determine whether it's a function or not? So there's a simple test called vertical line test. So what we do is, if it is possible for a vertical line to cross a graph more than once, okay, then the graph is not the graph of a function. So for example, if we have something like this, okay, now if I draw a vertical line here, the vertical line cuts the graph at 2 points, so this is not a function. But if I have something like this, okay, now if I, no matter where I draw the vertical line, it cuts the graph only at 1 point, so this is a function. So that's how we can differentiate between function and non-function graph using the vertical line test. So let's look at some examples here. The first one, it looks like it's a graph of an ellipse. So if we draw a vertical line like this, it cuts the graph at 2 points, so this is not a function, so no. Now here, in this one, if you draw a vertical line, no matter where you draw the vertical line, you can cut the graph only at 1 point, so this is a function. Now, same thing here. If you draw the vertical line, it cuts the graph only at 1 point, so this is also a function. And here, see, there's a vertical line cutting the graph at 3 different points, so this is not a function. So that's how we can determine whether a given graph is a function or not a function using the vertical line test. Now, the next thing that we are going to look at is how to find the domain of a function if we are given the formula, okay? If you are given a formula, so how do we find the domain of a function? So there are 3 different cases that we are going to look at. The first one is the polynomial function. So polynomial function means it's an algebraic function where the exponent of x are whole numbers. So for example, f of x equals 3x squared plus 5x plus 2. So this is a polynomial function because the exponent of x are whole numbers. So here we can write x to the 0, which is still a whole number. But if you have p of x equals 3x to the 3 half plus 5x plus 2, then this is not a polynomial function because this exponent is not a whole number. So you know what a polynomial function is. So if a function is a polynomial function, then the domain of that function is all real numbers. So that means we can take any real number as the input for that function. Okay, so usually we write all real numbers as in the interval notation as negative infinity to infinity. Or if you write that in set builder notation, then we write x as that x is an element of a real number. Now that's how we find the domain of polynomial function. That means all real numbers. The domain of the rational function is also set of real numbers such that the denominator is not zero. So all the x value that does not make the denominator zero is in the domain of the rational function. Or we cannot take the x value which makes the denominator zero. Okay. Now domain of radical function where you have a square root or cube root or fourth root or fifth root, this type of functions. Okay, so they are radical functions. So the domain of radical functions is given by these two things. Okay, so the first one, if this root is odd, so for example 3 5, then the domain is all real numbers. Okay, because you can find the root of the negative number if the root is odd root. Okay, now but the domain of a radical function when n is even, that is a square root or fourth root or sixth root, in that case we cannot have a negative inside the root. If we have that, then we don't get a real output. So for that case we must have the inside, this inside quantity non-negative. So for those functions, the domain is all x value such that the inside function, I mean the inside quantity is not zero. Or all x value that does not make the inside quantity negative. Okay, it should be non-zero. So let's look at some examples for this. The first one is a rational function. So we know that for rational function, we cannot have these negative, or we cannot have x squared plus 2x minus 3. It should not be 0. That's what we are looking for. Okay, but it's hard to find all the numbers that make this quantity non-zero because you will have infinitely many numbers. So what we do is we'll find the numbers that make this quantity zero. So what we do is we are going to write x squared plus 2x minus 3 equals 0, and we'll find the value of x that make this quantity 0. And then when we write the domain, we'll just avoid those numbers and list the domain. Okay, so let's go ahead and first find the value of x that makes this 0, or let's go ahead and solve this quadratic equation. So we can easily factor this, which is x plus 3 times x minus 1 equals 0, or that gives us x equals negative 3 and x equals negative 1. That means this quantity is 0 when x is negative 3, or this quantity is 0 when x is negative 1. Or in another word, we can say this function is undefined if x is negative 3 and, sorry, this is positive 1. X is positive 1. Okay, so this quantity or this function is undefined if x is 1 or negative 3. So that means these two numbers cannot be in the domain of this function. So what we'll do is we'll just draw the number line. Okay, so we have negative 3 and 1. So what this says is we cannot have this number in the domain. That means everything other than negative 3 and 1 are in the domain of that function. So all the numbers right here, all the numbers right here, and all the numbers right here are in the domain of that function. So this is how we are going to write that in interval notation. So the domain is negative infinity to negative 3, and then we'll write union of negative 3 to 1, union 1 to infinity. And this is called interval notation. Okay, um, so this is called interval notation. Okay, interval notation. So you really have to be careful. So when we write these type of parentheses or this type of bracket, so this means the endpoints are not included. So if we have a bracket, then the endpoints are included. Okay, so here that's how we write the domain in interval notation. So if you have to write that in the set builder notation, then this is how we are going to write it. So domain are all the x values such that x is not equal to -3 and x is not equal to 1 and x is an element of the real number. So that's how we write this domain. Now let's look at another example where we have a square root. So remember, for the square root, we say that this quantity cannot be negative, or it has to be non-zero. So this is how we are going to write that. So for the domain of this function, 9 minus x squared must be greater than or equals to 0, which means it cannot be negative. Or this can be written as 9 is greater than or equals to x squared, or that can be written as x squared is less than or equals to 9. Now in order to solve this, take this square root. So that gives us absolute value of x is less than or equals 3, which means x is in between -3 and 3. So that means in the number line, we have -3 here, we have 3 here. So the x values are from -3 to 3. So we have equal sign here. That means we include those endpoints. So our domain in the interval notation is -3 to 3. Or in set builder notation, we write this domain as x such that x is between -3 and 3 and x is an element of real number. So now for the third one, it's a little bit interesting. We have to take care of two things here. One, it is a rational, so this one cannot be 0. And then we have a square root, so the inside quantity must be non-zero. So that means, so inside quantity must be non-zero, but it cannot be 0 because of the first condition. So that means what we have to do here is this quantity inside this square root must be strictly greater than 0. See the difference between what we have here and here. So in this case, we could have greater than or equals to 0 because it's not in the denominator. But here, since this quantity is in the denominator, we cannot have 0 as well. So it has to be strictly positive. So let's go ahead and solve this inequality. So -4x, if you add 8 on both sides, so you get 8 on the right hand side. Then if you divide by -4, then we get x is less than -2. Remember, when you divide by a negative number, if you divide by a negative number, the inequality flips. Okay, so we get x is less than -2. That means the domain of this function is -infinity to -2. So if you draw the number line, so it's right here. Here's the domain. Now in the set builder form, this can be written as x such that x is less than -2 and x is an element of real number. Okay, so that's how you find domain if you are given the formula for the function. Now if you are given a graph, how do you find the domain? So and range. So the domain means when you are given a graph for the domain, you are going to look at um, how small the x value is possible for that function and how large is the x value possible. So for example, you look from left to right or sideways. So if you look at the graph, the left end of the graph is right here. So graph goes from this end to this end. So that's where the domain is, from left to right. So this is the domain. It goes from -1 to 3. So when you write it, you just have to be a little bit careful whether we can include the endpoints or not. Okay, so for example, it goes from, we know it goes from -1 to 3. We have a dot here, that means we can include -1, but there's a hole here, that means we cannot include 3. So domain is the interval, so it's a close on the left and open on the right. So that's the domain. Now for the range, you look top to bottom, or what's the smallest value of the functions right here, and what's the largest value, or how far on the top does the function go. So it's right here. So this is the range. Okay, so range of this function goes from -5, but again here is a hole, that means we cannot include -5. So it's open interval for -5, and then it goes all the way to 4. Okay, so if you look over there, it goes through 4. We put dot only at the endpoints. It's not the endpoint of the graph, it's just a regular point on the graph, but we clearly see that it goes through 4. That means 4 is, the value 4 is on the graph. So that means this is 4, and we close this. Okay. Now for this one, domain, left to right, this function goes forever. That means it goes forever on the left. Similarly, that function goes up forever. That means the x value goes forever on the right. So that means the domain is -infinity to +infinity. And the range, same thing, it goes below, it goes down forever, and it goes up forever. That means the y values are also all real numbers. Now for the third graph, the graph goes from this point towards right forever. That means the x value goes from here to the right forever. That means the domain goes from 2 to infinity. Now for the range, let's see, the lowest point on the graph is right here. That's the lowest point on the graph. Since it goes forever this way, so the highest point does not have a bound, it goes forever. So that means the range is from -2 to infinity. So that's how we find domain and range from the graph. Now the next thing that we are going to look at is how to evaluate a function, or if you are given an input, how do you find the output when you are given a formula for the function. So here we are given the formula for the function, which is right here. Okay, now we are given the input, so this is the input of the function f of 0. So when x is 0, or when the input is 0, what is the output for the function? So in order to do that, in order to find the value of the function, what we do is we just substitute x with whatever input is given to us. So for the first one, for f of 0, I'm going to substitute x with 0. Okay, so that's what we are going to do. So f of 0 equals 3 times, so the value of x is 0, squared plus 5 times 0 minus 2. And that gives us, so 3 times 0 squared is 0, 5 times 0 squared is 0, and then we have -2, so it's -2. That means f of 0 equals -2. Now that's A. And B, f of -2, we do the same thing. So we'll take that -2 and substitute for x. So 3 times -2 squared plus 5 times -2 minus 2. So -2 squared is 4 times 3, 12, minus 10 minus 2, and that gives us 0. So that means f of -2 equals 0. Now C, we have f of 5a. That means our input is 5a. So which means we are going to substitute x with 5a. So that equals 3 times 5a, the quantity is squared, plus 5 times 5a minus 2. So that gives us, so 5a, the quantity squared is 25a squared, plus 5 times 5 is 25a minus 2. That gives us 75a squared plus 25a minus 2. So f of 5a equals that. Now let's look at the last one. We have f of b minus 2. So what we do is we are going to go ahead and substitute x with b minus 2. So 3 times b minus 2 squared plus 5 times b minus 2 minus 2 equals, so here the first one is b minus 2 times b minus 2, so which is, you can do that, you can FOIL it. I'm going to write it here. So b squared minus 4b plus 4, and then distribute that 5 here, so you get 5b minus 10 minus 2. Now let's go ahead and distribute that 3, so we get 3b squared minus 12b plus 3 times 4 is 12 plus 5b minus 10 minus 2. Now if you combine the like terms, then we get 3b squared minus 7b, and then 12 minus 10 minus 2 is 0. So f of b minus 2 equals 3b squared minus 7b. So that's how we evaluate any function. So this is D. Now the next thing we are going to look at is a piecewise function. So sometimes like here we have a formula for the function, but sometimes we need more than one formula to represent a function. So if we have that, then that's what a piecewise function means. So we have, for example, if you have f of x equals x squared if x is greater, sorry, x is, let's say, less than 0. Okay, so if we have something like this, less than 0, then x if x is in between 0 and 5, or constant 1 if x is greater than or equals to 5. So if you have something like that, we have PCS of function for different intervals in the domain. Okay, so that type of function is called piecewise defined function. So we'll look at example for that. So here, so you really need to understand this, okay, what does the piecewise function mean? So if you look, this is very important here, this domain here, okay? So if we draw a number line, okay, if we draw a number line, so the number that we have there is number -4, and then we have 1. So what does this mean is when x is less than -4, okay, that open parenthesis. So if x is less than -4, or if x is here, then the function is f of x equals 1, which is a constant function. So no matter what x value we pick from here, the value of the function is 1. The second one is if x is in between -4 and 1, such that -4 is included, so we have a bracket here to 1. So if x values are on this interval, then the definition of the function is f of x equals x plus 2. So if your input is in this interval, this is what we use to find the value of the function. If the input is in this interval, this is what we use to find the value of the function. And the last one says if x is greater than or equals to 1, so if the x value is greater than or equals to 1, so if the x value is right here, then the definition of the function is f of x equals x minus 2 squared. Or if your input is here, which is greater than or equals to 1, then we use this definition of the function to evaluate the value. Okay, so let's go ahead and do this example here. So we are asked to find f of -5. So I know that -5 is in this interval or right here. That means when x is -5, I'm going to use the first piece of the function, okay? The first definition. So this is a constant, f of x equals 1. That means no matter what x value I have, it's always going to be 1. So it's just 1. Now f of -4, so you really have to be careful here. This one says x is less than -4. That means if x equals 4, then it's not in the first interval, it's in the second interval right here, or right here. -4 is included here in this interval here, okay? So that means we have to use this definition of the function of the second one, which is x plus 2. So x is -4 plus 2 gives us -2. Now f of 0, again 0 also belongs to this, it belongs to the second interval here, so we use the same definition of the function. That also gives us 0 plus 2, which is 2. Now f of 1, again just be careful here, 1 does not belong to this interval because x is less than 1. So x is greater than or equals to 1 right here, that means 1 belongs to this interval here, or we have to use this definition of the function. So f of 1 equals 1 minus 2 squared. So 1 minus 2 is -1, when it's square -1, you get positive 1. So f of 1 equals 1. Okay. Now the last one is f of 10. So f of 10 means again we have to use this last definition or last formula. So f of 10 equals 10 minus 2 squared. 10 minus 2 is 8. 8 is squared is 64. So f of 10 equals 64. So these are the different values that we are requested to find. So that's how we evaluate a piecewise function. So in the next slide, we'll go ahead and graph this piecewise function. Okay. So for graphing, what I usually suggest is we have three different pieces here. So we'll make three different tables and we'll put that on the graph. And that's the easy way to graph this, okay? So let's go ahead and make the table for the first piece again. The first one, whenever x is less than -4. So if I draw that number line, so we have -4 and 1. So we are talking about these values right here, the first one. So for x less than -4, the function is f of x equals 1. So let's go ahead and make a table for that. Okay. So let's take some x values and find f of x. So I always like to start from here, though -4 is not included in that interval, but I'll still start from there. Okay. So I'll take x equals -4. It's always 1, so it's 1. And then I just put a mark here because this is a special case. We cannot take that value in that piece, but I still start from that endpoint. Okay. Now the next one, since we are going to the left, so -4, and then we go to the left because this is x less than -4, so the next number could be -5. If I take -5, still it is 1 because it's a constant function. -6 is still 1. -7 is still 1. So no matter what I take, I'm always going to get positive 1 as the output. Okay, so that's for the first piece. Now for the second piece, x is in between, so let me use a different color. So for the second piece, x is in between -4 and 1, where -4 is included, and the function that we are going to use, the definition is x plus 2. So let's go ahead and make a table for this one as well. Okay, so here we'll start from this endpoint and we'll go to 1. Okay, so we'll start from -4. So when we take -4 and plug it in here, we get -2 as output. So we are going to use this. Okay, so the next number we are moving to the right from -4 because x is greater than or equals to -4. So the next number is -3. When I put it here, I get -1. If I take -2, I'll get 0. If I take -1, I'll get 1. If I take 0, I get 2. And if I take 1, I get 3. But this is a special case again. Okay, so I'm going to circle this because 1 is not included in that interval. So that's why I still put that value endpoint, but I'll just mark it here. Okay, so we have to do something with that when we draw the graph. Now the last one, let's go ahead and to the last one, which is x greater than or equals 1, and then the function for that is x minus 2 squared. So for that, okay, so for that, let's start from 1. So 1, when I take 1 and put it here, so 1 minus 2 is -1 squared is 1. If I take 2, I get 0. If I take 3, 3 minus 2 is 1, squared is 1. If I take 4, I get 4 minus 2 is 2, squared is 4. And if I take 5, I get 5 minus 2 is 3, squared 9. So let's stop here, okay? Now let's go ahead and graph this one. So let's start from the first piece. So for the first piece, when x is -4, y value is 1, but what I know here is I cannot include that value here. I cannot put it into the graph because that does not belong to this interval, okay? It's in here. So what I do here is I'll still start from that point, but what I do here is since I cannot include that, so I'll put a open circle here. That's the reason that I still use it, okay, to make that open circle. And then when x is -5, it's still 1, -6, 1, -7, 1. It's a constant function, so this is how it's going to go. So that is the graph of the first piece. Now let's move on to the second piece. So the graph for the second piece, when x is -4, it's -2. So when x is -4, y value is -2. And I'll make a solid dot because -4 is included here. Okay, in this case I made an open circle because that -4 was not included in this interval. So then when x is -3, it's -1, y value is -1. When it's -2, 0, -1, 1, 0, 2. And when I hit 1, it is 3, but I cannot include that on the graph. So when x is 1, it is 3, but I cannot include that on the graph, so I'll put a open circle there. So that means the graph for the middle piece is this line from here to here. Okay, that line. Now for the last one, when x is 1, it is 1. So let me use black. So x is 1, the value of the function is 1 right here, and I put a solid dot because 1 is included in that interval. Then when x is 2, it is 0 right here. When x is 3, it's back to 1. X is 4, it is 4. When x is 5, it is 9, so somewhere up here. Okay, now I clearly know that this is not a line, it's a parabola. I have x squared, so I'm going to draw that as this, and then that goes forever. So that's how I draw the that's how we graph a piecewise function. Okay, so the next thing we are going to look at is intervals where the function is increasing and decreasing. So if function is increasing, if, so the simple definition is, this is the simple definition here. Okay, if f of x1 is always less than f of x2 when x1 is less than x2. So that means when you have a graph, okay, so something like this. So if I choose x1 and x2 so that x1 is less than x2, then the corresponding value of the function has the same order. So if x1 is less than x2, then I have f of x1, which is this height, less than f of x2. So if that happens in any interval, then the function is increasing. So the simple way to say that when we look at the graph is when we go from left to right, if the function rises, then the function is increasing. So here the function is rising, so the function is increasing. And if the function is dropping down when we go from left to right, then the function is decreasing. Or the mathematical definition is, if I choose x1 here, x2 here, so if x1 is less than x2, then this is opposite here. F of x1 is greater than f of x2 if the function is increasing. Okay, so this height here is greater than this height. So if that happens, then the function is decreasing. Now a function is constant if it is not rising or falling, if it just has a horizontal straight line, okay, like that, then the function is constant. Now, when the function is increasing, decreasing, then we have something called local maximum and minimum. Okay, so for example, let me draw a graph here. So if I have a graph like this, okay, so the function is increasing here, reaches to that point and decreases here. That means this point is the local maximum. Okay, or if I take a small interval, the highest value of the function in that open interval is what the local maximum is. Similarly, if the function is decreasing and turns to increasing, then that turning point represents the local minimum. Or if I take a small open interval, the minimum value of the function in that open interval represents the local minimum. And in general, we call local max or local mean as local extrema. Now let's look at an example. So here we have an example. So let's go ahead and find the intervals where the function is increasing and decreasing, and then local max and min. Okay, so if you look over here, when we go from left to right, so when you go in this direction, then we see that, so when we go from left to right, the function is rising up here. So see, the function is rising up here up to this point. And then the function is dropping down here. From here to here, the function is dropping down. And again, the function is going up from here, okay, rising up when you go from left to right. So when you are walking on the x-axis, you are climbing up on the function up to this point, and then from that point, when you keep walking to the right, the function drops all the way to here and then again increases. So that means we have the function, the interval where the function is increasing on this interval right here and then right here, that is increasing, and this middle piece is the decreasing. So when you're writing the interval where the function is increasing, decreasing, you're writing the domain or the x value. So you're saying the function is increasing on these x values or these intervals. So the interval where the function is increasing, we have two intervals for that. One is right here, so this one. So the x values here is from negative infinity all the way to this x value here, and the x value is not 2, it is 0. So increasing on negative infinity to 0. And then there's another interval where the function is increasing, which is from here, the x value is 2, so from 2 to infinity all the way to the right. And always we write the open interval, that's the definition, okay? A function increases or decreases on that open interval. Now the function is decreasing on the interval from here to here. This part is decreasing, so from 0 to 2. Now from the graph, we can say that the peak is the maximum, local maximum. So here is the peak, so the local maximum is here, and the dip is the local minimum, and here is the dip, which is the local minimum. So local max equals the y value here, which is 2 at x equals 0. So the x value is 0, y value is 2, and the local minimum, okay, local mean equals this value, which is negative 2 at x equals 2. Okay, so we'll just stop here for this video, and then in the next section we'll look at more information about the function.